Well, thank you, Sanket. I'm Maika Takita, and thank you for coming to our Dynamic Circuits and Error Detections seminar. So I'm very excited to be able to share new dynamic circuits capabilities that now we are reintroducing as utility-scale dynamic circuits. So first, what is a dynamic circuit? When I say the word quantum circuit, it's likely that many of you have pictured in your mind something like what's on the left-hand side, where I apply a sequence of single and two-qubit gate unitary gates and make terminal measurement at the end. However, on IBM hardware, we have access to a broader set of resources than just unitary gates. We have components like mid-circuit measurements, classical computation, and even feedforward, where we take the result of those mid-circuit measurements and feed them into the logic of now classically controlled gates to apply next. Taking this broader set of resources all together allow us to build dynamic quantum circuits, which are extremely powerful, as unlike static quantum circuits, we can implement any allowed quantum process, not just unitary evolution. And while we know the building dynamic circuits is an essential ingredient from quantum error correction, it is also interesting to ask, can they be used to discover and realize new quantum algorithms and applications along the way? So, dynamic circuits are clearly more general than static circuits, but what makes them promising tool in the near term? To illustrate this, let's consider the space-time resource needed for a quantum circuit, namely spatial resource, or the number of qubits required, and temporal resource, or depth of the circuit. Dynamic circuits have been shown to be useful in reducing both of these types of resources. In particular, the ability to reset and reuse qubits can drastically reduce spatial overhead in certain situations. A simple example of this is in the following staircase circuits, where we apply a sequence of two-qubit unitaries and make terminal measurements. Naively running this circuit requires n qubits. However, we can notice that on the left-hand side, each qubit isn't used at all after the staircase until the measurement. Then we might as well move the measurement up as far as possible, and once we do that, we might as well just reset and measure qubits and use it for the next step of the staircase. Putting this together, we see that the results on the left-hand side circuit are entirely equivalent to the results of the right, which needs only 2 qubits, independent of how big the staircase is. This is just one example of how dynamic circuits can be leveraged to drastically reduce the number of qubits needed to implement quantum circuits with certain structures. However, they are not only helpful for reducing spatial resources, but it can additionally reduce temporal resources or depth needed for certain problems. A great example of this is in preparing the GHZ state, which is the equal superposition of all zeros and all ones. To make things simple, let's imagine we want to prepare the state on a 1D line. Then, if we only have static unitary circuits, the best we can do is the circuit on the left-hand side, which prepares the state by starting from the center and grow the correlation in both directions with the ladder of CNOT gates. This circuit requires a depth that is linear in the size of the state, so bigger GHZ states mean we need a deeper and deeper circuit. The reason for this is fundamental. There is a speed limit for how fast we can unitarily spread correlations. And in this circuit, we are spreading those correlations at a maximal speed along the edge of a light cone. However, with dynamic circuits, we can completely break this speed limit. In particular, by strategically leveraging mid-circuit measurements, classical computation, and feed-forward, you can prepare a GHZ state in constant depth, meaning the depth is completely independent of the size of the GHZ states. 1,000 qubit GHZ state requires the same depth circuit as a 10 qubit one. The way we do this is with the circuit on the right, which is a bit more difficult to parse, but the high-level idea is that we are preparing lots of little GHZ states and then fusing them together with measurements. Then, Because the measurement outcomes are inherently probabilistic, we apply X gates to make local correlation on the state condition on those outcomes. Altogether, this ability to reduce circuit depth is one of the most powerful features of dynamic circuits, and it's why we are so excited to bring our new dynamic circuits capabilities to you. There are already many neat ideas for how these capabilities can be used to explore different applications. These range from the preparation of wide variety of states to realizing certain non-unitary processes. You can even more efficiently compile certain unitary primitives by using non-unitary gates, ingredients. In this talk, I will focus on state preparation and, in particular, show how the new dynamic circuits capabilities can leverage to improve the preparation of a many qubit entangled state known as the AKLT state. First, what is the AKLT state and why prepare it? It is a historically important state that describes a spin chain composed of spin 1 particles, which we can encode using a pair of qubits per site. This is the prototypical example of both a matrix product state as well as symmetry-protected topological order, which lends it a number of interesting exotic features. It is also a useful resource state for tasks such as measurement-based quantum computation, and most importantly, in the context of today's talk, with unitary circuits, the prototypical way to prepare it is with a linear depth unitary circuit. However, with dynamic circuits, this can be reduced to a constant depth circuit, an impossibility with static circuits alone. The preparation of this state of IBM hardware was first presented at the IBM Quantum Summit in 2022. At the time, experiments were limited to up to 6 spin 1 site, requiring 40 qubits total for unitary-based preparation, and 18 qubits for the measurement-based scheme, with the additional 4 qubits being needed for fusion measurements. At the time this paper was published, only post-processing was possible, meaning no active feed-forward was used, and all correlations on the state were done virtually in post-processing. The dynamic circuits capability that we introduced at the summit in 2022 enabled this experiment to run with real-time feed-forward. But this inherently came with certain limitations. In particular, the previous version of dynamic circuits required conditional operations to be done sequentially, but which added around 700 nanoseconds extra latency per if statement. But with the introduction to switch statement later on, allowed for almost parallel feed-forward operation, but only up to 10 bits. In the context of the AKLT state, this meant we could only prepare up to a 12-site AKLT state within a reasonable latency. Furthermore, there was no differentiation between the terminal and mid-circuit measurements. And the circuit timings were non-deterministic, so we were not able to make use of the feed-forward time, but just wait. This prohibited applications of any instructions during the idling time and made it difficult to implement error suppression techniques, such as dynamical decoupling, in the non-static part of the circuit. Lastly, from a user perspective, it was opaque. There was no way to obtain the scheduled circuit, nor visualize it. In the new dynamic circuits release, we are happy to have resolved many of these challenges. And rather than relying on a switch statement, user can now implement parallel if blocks, which in our example, enable the preparation of 30-site AKLT state involving 90 qubits, with only single overhead for all the feed-forward operations, rather than applying them sequentially. To put some approximate numbers, with the previous version of dynamic circuits, that would have taken more than 20 microseconds longer to prepare a 30-site AKLT state. A new mid-circuit measure component has been added, which enables faster, independently calibrated measurement for these types of circuit. The stretch instructions provide users the ability to have greater control over timings, enabling the implementation of dynamical decoupling during feed-forward time. And finally, scheduled circuit can now be visualized, a helpful tool for debugging and optimizing circuits. So, to demonstrate how all these new capabilities lend themselves to new possibilities with dynamic circuits, let's dive into the specific example of preparing the AKLT state. There are a number of different methods for preparing this state, but today we will focus on a unitary-based version, a measurement-based approach where we do not use dynamic circuits, but instead make any correlation in post-processing. We note that this does not prepare the actual state on hardware in a fixed basis, but is instead like preparing it in a local basis that is determined on the fly by the measurement results. Nonetheless, it can give a sense of how well the different components of the circuits are working. And third, a measurement-based approach that uses actual dynamic circuits with real-time feed-forward. And finally, a hybrid approach that blends unitary and dynamic circuits techniques. From method to method, there's a space-time trade-off in that the measurement-based approaches drastically reduces the depth of the circuit, but requires a greater number of qubits to carry out the fusion measurements. On top of these, we can use different features to inspect and improve the preparation, including parallel ifs, different measurement types, stretch DD, and the visualization of timings. In the following slides, I will walk through these different options and show how they impact the preparation. To verify the preparation of the AKLT state, we will look at an observable called the string order. Its exact mathematical form isn't so important, but the key thing to take away is that it is a non-local observables that extend across the string of length L, which we can tune. And it is expected to take on a non-zero value for the AKLT state, which you can think of as the fingerprint of its topological order. To generate a 30-site AKLT state, we need 60 qubits with extra ancilla qubits. Let's pick length 10 string order as an example. On an n side of 30, there are 21 unique length 10 chains that you can sample from. Throughout this talk, I will use n side of 6 example for visualizing the circuit while using n side 30 data to describe different methods you can use to prepare the AKLT state and how the new dynamic circuits feature come into play when optimizing circuit generations. So, let's start with state preparation with unitary-only circuits. With unitary gates, you can generate AKLT state in this ladder form, just like you might with GHD state preparation. Each of these red blocks constitute of 3 qubits, where you need 7 layers of CZ gates, along with 10 single qubit gates. By using fractional gates, you can reduce the number of 2-qubit gates down to 6, but for this talk, I will only show results without using fractional gates. In Qiskit, you can use the circuit drawer to see how the circuit depth might grow, but this type of drawing doesn't have any concept of timing. While there are tools such as timeline drawer, you can use for static circuits, it doesn't return the absolute timing that the low-level compiler might generate. So let's see how this circuit might look using a new visualization tool that is returned with the job result. This tool can help you optimize and debug your circuits. To the right is part of what a job result can return to users in its metadata. Here, the qubits are ordered in physical qubits numbering, top to bottom. So it doesn't quite look exactly like the way it looks to the left that are drawn with the virtual qubits ordering. But these green blocks represent 2-qubit gates, while purple blocks are from measurement instructions. And the bottom shifted purple block represents measurement capture. As you see and would expect, as you increase the number of sites in the ladder, the depth of the circuit will increase. Circuit durations and another information you can pull from the metadata returned with job results. You can learn more on how to use this beta feature during the tutorial session this afternoon. Now, let's see what the string order of length 10 at n side is 30 looks like. When preparing the circuit unitarily, you need 62 qubits, and the total duration of the circuit is over 16 microseconds. Looking at the histogram of length 10 string orders, you see that there's a wide distribution of the expectation values across 21 different chains, but all non-zero, which is where we want to be. Now, by using measurement-based approach, you can generate AKLT state in post-processing with constant depth. With this approach, you need more ancilla qubits to do so. For n side equals 30 example, we now need 90 total qubits. But as you can see in this circuit, there's only one layer of red blocks. And as you increase the number of n site, you increase the number of ancilla qubits, but not the depth. Now, you can check out the scheduled circuit for this too. And in this scheduled circuit, all the measurements, including the ones used for fusion, are played simultaneously with terminal measurements, making this circuit very shallow. Here I'm showing all 30 pairs of qubits used for 30 n sites circled in black. And you can see extra qubits in between that are used as ancilla qubits. The circuit to generate with this approach only took 3.8 microseconds, which is more than 4 times faster than unitary-only circuits. Looking at length 10 string orders histogram counts using measurement-based approach, you can see that the distribution going down closer to the ideal value of minus 0.45 with smaller spread. Now, let's see how this looks when you add real-time feedforward. Here's a circuit for n side is 6, prepared using dynamic circuits. Inside the conditional operations, now we have a swap operation for correcting X defects and conditional Z for correcting Z defects. Here, conditional swap adds additional 3 2-qubit gates and 3 single-qubit gates on top of the feedforward time. Using the scheduled circuit visualization, we can inspect how long the feedforward operation is in this example. Let's go through the circuit section one by one. First, the static part of the circuit consists of single and 2-qubit gates. Next, a layer of measurements in orange, and a new key in green at the bottom called broadcast. This green broadcast block overlaps with the orange capture block, but extend by some amount to allow for time to classify the measurement outcome and move measurement results around to be used for conditional operations. After broadcast, we have receive at the top of the visualization, which is when the controllers are ready to process measurement results and apply feed-forward operations. The time after receive depends on the complexity of the classical operations, but soon after receive, conditional operations, in this case a swap operation with 3 2-qubit gates, are applied. Finally, we have a terminal measurement layer at the end. So before showing the string order results using this approach, I want to introduce how you can use stretch instructions to apply error suppression techniques such as dynamical decoupling. Okay, so let's zoom into the measurement and conditional operation region here. Each of these red blocks represent a stretch delay of some duration. First, we can define stretch delay of S. Then you can insert stretch, pi, stretch, pi, stretch to apply a 2-pulse dynamical decoupling sequence during the idle time before conditional operations are applied. Instead of applying the stretch S twice in the middle, you can also define a new stretch that is twice as long as stretch S. And again, you can learn more on how to use stretch during the tutorial, but let's see how this looks after scheduling. Looking at the scheduled circuit, you see pi pulses are applied after a delay, another one after 2 times that delay, and followed by another delay before the conditional swaps are applied. This is one example of how you might want to schedule a dynamical decoupling sequence during the feed-forward time. Now, let's look at the string order result of AKLT state preparation for large n site that was enabled with new parallel if and stretch DD features. The circuit of this size now takes around 8 microseconds, including real-time feed-forward and conditional swaps. And you can see the histogram of all length 10 chains in purple. Now, you might think it went further away from the post-processing result, but when we run the post-processing approach, we did not have a fair comparison. With dynamic circuits, on top of feed-forward operation, we have to apply mid-circuit measurement and terminal measurements in 2 layers. To make a fairer comparison, I run post-processing version of the circuit generation, splitting the measurement in 2 layers back to back. The results are shown in pink histogram, showing errors associated with simple change. So let's review different methods we've looked at so far. Unitary circuits taking over 16 microseconds, post-process going from 3.8 to 6.4 when splitting up the measurements, and 8 microseconds when adding real-time feed-forward, including the expensive swap operations applied conditionally. So we still haven't used all the new features yet. And now, let me introduce different measurement types to this circuit. And let me say, this is one of my favorite additions to our capabilities. In the mid-circuit measurement layer here, you can now choose to use the new mid-circuit measure instruction instead of default measure. Our new mid-circuit measure instruction is tied to a new measurement called measure 2. And we have calibrated so that they are faster and suitable for mid-circuit. Here, the original circuit, where default measurement capture length is 1.44 microsecond. Now, using a new mid-circuit measurement instruction, the circuit is shortened by almost a microsecond. Here I'm plotting out assignment errors, comparing the default measure in purple and measure 2 in orange on the 90 qubit strings that I used for this experiment. As you see, the error goes up slightly for measure 2, but not by a lot, maintaining sub 0.5% error median for both approaches. Now, using this approach, we now have a circuit duration of around 7 microseconds, and this can further bring down the string order of length 10 chain plotted in orange. Finally, I want to share a hybrid approach that utilizes the idle time during the feed-forward operation, another new feature that I'm very excited about. Here, for an n site is 6 example, we can split up 4 sites to be prepared with measurement-based approach, and 2 extra sites extending one to the left in the circuit, adding on the top, and one to the right, added to the bottom. And these gates are applied while we have this idling time for measurement and feed-forward. So there's no extra cost in terms of depth associated with it. In fact, using this approach reduces the number of qubits needed, while also reducing the duration slightly as we decrease the classical complexity. For n site is 30 example, I added 2 sites each in both directions, so total of 26 measurement-based and 4 unitary approach. This approach required 86 qubits and further decreased the length 10 string orders, shown in green histogram. Now, I want to show one more set of data, and I promise this is it, and summarize my observations. DD or no DD? That is the question. All the data that I've shown so far have been with dynamical decoupling inserted in both unitary section of the circuit and non-unitary section using stretch DD. The right column of data is equivalent to what I showed earlier, but without DD. Note that I have now changed the x-axis as the results were worse without, as you might expect. But the biggest impact was, in fact, on unitary circuits. Without DD, the mean string order was much higher and performed a lot worse than measurement-based and dynamic circuits approach. The impact is smaller, but we do see some improvement in stretch DD on dynamic circuits method. Now, I'm not claiming that dynamic circuits is beating the unitary approach in this example, but the main point I want to highlight is the spread of string order across the long chain. You see the unitary case on the bottom, DD or no DD, have large spread, which is pointing to the fact that we might not be preparing the states as evenly as we'd like. Using the measurement approach and layering the gates, having shallower depth circuit is getting us to a good or sometimes better result with much tighter bounds. I am very excited to see this trend, and on top of that, the fact that we are still seeing a good signal without any type of error mitigation, to me, is a great sign that we're on the right track. So let's summarize. Here's the AKLT state preparation. We have looked at preparing for 4 different types of preparation, with unitary circuits, to measurement-based approach, with and without dynamic circuits, to hybrid, combining unitary and dynamic. I have shown the features with parallel ifs for larger state preparation and different measurement types that really improved dynamic circuits example. I've also introduced stretch DD that we could use during the idling time, where it's being measured and feed forward. And finally, this beta version of visualization is really helpful for optimizing and debugging our dynamic circuits generation. So, in summary, I have introduced 4 new features that we added to our dynamic circuits capabilities that now we are very happy to reintroduce as utility scale dynamic circuits. Please check out the documentation, but then also this afternoon, there will be a tutorial session, and you'll learn a lot more on how to use these new features. Thank you. So next, we have my colleague, Ali Reza, speaking on using error detection to our quantum circuits and sharing very exciting results from that.